Hello. Now, so we're waiting tomorrow or? Sorry? We can wait, okay. So today I will speak some things we didn't manage to mention before what we are planning. Yes. So even from the first day, we have some material to speak about. Have you ever heard about Nordhus Gaddum theorem? You know what is it? It's a very classical theorem. If you suppose that we do it first day, Adina will do it, and then I came on time, and so there's a famous theorem, and very recurring, people invent somebody is trying to prove this theorem. So if you have a new coloring, you should try, can you prove it for your coloring, this theorem. But let me mention, one time, maybe like Nordhus and Gaddum. Is it maybe Gaddum Indian name? No. Theorem. For every graph on n vertices, the following holds. If you take the sum of G, a chromatic number of G and of its complement, then at least okay, this is A, this is B, and if we try to multiply them, then we're gonna have okay, we will prove this and this, okay, and the other two follows by arithmetic, geometric means and so on immediately, okay. These two we're going to prove, and the other two you're going to prove at home, yes, or afternoon, yes. So, okay, let's prove this first because this is easier. Okay? Look, let's see proof. B, this one. So, let C1 is optimal coloring of G, and or just C, let's say it's C, and let C bar is optimal coloring of G complement. Okay. Now for every vertex in G or in G complement, whatever you like, we define coloring, new coloring. Okay. C star of V will be two tuple, coloring of V, the color of V, and the other coloring of this, yes. Okay. Then it is easy to see that, do we agree C star is proper coloring of Kn? Yes, because here's our graph, and we have, let's say, two vertices. If they are connected in G, if this H is in G, then C star is, and C star V are different in which coordinate? In the first coordinate. And then they are different. If they are first different in the first, then they are different. And what if U and V are adjacent in G complement? That means they are not adjacent in G. Then these two, instead of writing, I will copy paste. And we use the color blue. In the second coordinate, yes? So, these two colors are different. They are different in the first coordinate if the H belongs to G, and they are different in the second coordinate if the H doesn't belong to G. That means belongs to G complement, yes? So this way follows, we have done this. It's a proper coloring of complete graph. How many colors we use in this tuple coloring? So this C star uses at most 3G multiplied colors. Yes? The number of colors use it in the first coloring, multiply the number of colors in the second color. It may not be equality, maybe we use less, because maybe we don't use every pair. But this is upper bound. And we have shown that it is a proper color of Kn. How many colors minimum we need to color Kn properly? N. So chromatic number of Kn, yes, is equal to N, yes, and this is here so we have so let's go to so we have from here that n is and this is this claim, and this is this claim, what we wanted to show. So next thing we'd like to prove that the sum of the chromatic numbers is bounded by n plus 1. When we have this bound and when we have this bound, these two follows immediately. We can try, but I think it's not necessary. It's like this arithmetic geometric means and something like that. So let's prove this bound. Let me copy this. So we want now to prove this bound. So we claim this bound holds. Yes. We will use a little bit degeneracy, né? Suppose that the genericity of G is K. Okay? And we will prove that the genericity of G complement will be at most n minus k minus 1. If we prove these two things, so we assume this actually. We assume this, and we will prove this. And when we prove this, then we have proven the claim. Why? Okay, let's see why this is true. So we assume this, and we assume that we can prove this, and then we can prove it. Why? Look, chromatic number of G plus chromatic number of G complement, they are smaller or equal coloring number of G plus coloring number of G complement. Okay? This is because chromatic number is always at most the coloring number. If we go this greedy coloring, and this one is, I think we define this degeneracy plus 1. Coloring, let's define it again. Coloring, let me explain here in a small box. We prove it, maybe the first day, maybe Professor Dino, maybe me, that chromatic number of G is always smaller or equal the genericity of G plus 1. Do you remember that? And when we prove it, then we say, okay, we defined this number to be coloring of G. Coloring number of G. This is just the genericity plus 1. This is the number of colors by which we can color graph very fastly, yes, in a way. Yeah? When we know the genericity, we can always, or coloring number, we can color with the coloring number colors fastly, yes. Of course, we need to know the ordering, yes. Okay, so I can clean this, yes. So, chromatic number is at most coloring number, chromatic number of the complement is at most coloring number of the complement, yes? Okay, and then what we have? Then we have k plus 1, coloring of G is k plus 1, if genericity is k, plus coloring of G complement is n minus k minus 1. I use here this, so n minus k minus 1 plus 1. Okay? And that will come n plus 1. That's what we want to prove, yes? So we have to, what we left to prove this. Okay? We will prove this by contradiction. Suppose this is not true. That means the genericity of the complement will be at least n minus k. So, let's go with other color. Suppose this is not true. Then the genericity of G complement. Okay? Now look like this. I will draw here graph G. I will draw here the complement. If I take the union, it will be complete graph. Do you agree? Now, look, since the genericity of G is K, we have subgraph H in G of minimum degree K, okay? So we have here graph H. Minimum degree of H is at least, because the genericity is D, we can assume it is exactly D. Yes? The genericity of graph G is D, then we have a subgraph of minimum degree D, yes? So in this H, all vertices of degree at least D, yes? And similarly, we have here a subgraph F, let's call it F, of what degree? A minus K, because we assume this is not false, so this is not true, then because of this. Because we have the genericity of G complement at least n minus K, here is of F n minus K. Now my question is, if I look these vertices in H and this vertices in F, can be some vertex in the both graphs?
They are all vertices of the complete graph, yes? Can we have a vertex x which belongs here, and the same vertex also belongs in F? Why not? Yeah, something like that. Let's see what happened. H in Kn. If x belongs to H, what means the degree? The degree here of H is at least D. What means if x belongs to F? The degree in G complement, which here of G and here of G complement, okay, will be at least n minus k. So look, these edges here are all different from the edges here, yes? Because this is a complement of G before it is. So that means that will imply that degree of the in the complete graph of H will be at least. I make some typos here. D is not D. D is K. Yes. Yes. Okay. Here's a K. Sorry about it. K. K. And this gives degree of x in the complete graph should be at least n. Which is not possible because a vertex in complete graph of order n may have at most n minus 1. Yes, exactly n minus 1, which is a contradiction. Okay, so what we have now? So what we know now? We know now that H and F are vertex disjoint. So it follows that vertex of H and vertex of F are the vertices have anti-intersection, yes? Okay? Now can you give me some bound of the number of vertices in H? If graph is degenerated, what is the number of vertices? At least?
At least K plus.
Exactly. Then size of H, order of H, how is it? At least K plus 1.
It's not possible that K is independence K plus 1.
K plus 1, but it is not possible.
It's not possible. So it's a start with K plus 4.
K plus 2, K plus
1 K plus 1?
repeat exercise.
It's
It's
exercise.
not critical.
So the exercise was K critical graph and not
We don't assume it's a critical graph. H is degenerated. K degenerated graph. This means every vertex has a degree at least K plus 1. So every vertex has at least K neighbors. And with itself together, this gives K plus 1. We don't assume that H is a critical graph. We never assume that. Okay? And similarly, what is the size of the V of F? At least. If it is minimum degree n minus k, it will have n minus k plus 1 vertices. Okay? Do you agree with me? Or you don't care? So, that, now we have that. Look, then the number n we know is at least VH VF, okay? They are vertices of Kn, yes? But disjoint vertices, so sum of the vertices together, union of the vertices, is at most n. But from other side we have, this is at least k plus 1, and this is at least n minus k plus 1. We have k plus 1 plus n minus k plus 1. It is n plus 2. Do you see contradiction? Is here anybody doesn't see contradiction? Okay, so we get contradiction. N cannot be bigger than n plus 2. This mean we have here this. It's not possible to have the genericity of G complement bigger than or equal to n minus k. So this holds, and then we apply this, and we get that. Okay? And so how will be the time? 9:26. Okay. This is one thing I wanted to say. There's another thing I want to say. Do you know what is? We ever study graph embedded on a surface? Not on the plane, on the sphere, but on the torus, projective plane. Do you know such things? So, just a little bit brief introduction. So, in the sphere, on the plane, we have the Euler formula V minus A plus F equal to 2, yes? And the sphere is ordinary plane, or just this, yes? But we have this thing here, how I drew it nicely. How I can draw it nicely. Torus. Do you know what is torus? Yes. We can have graph embedded on the torus. Okay. So your job is to find later for the next afternoon part a problem for you. Embed in how is spelling correctly? Embedding. Embed. E-M, so E? Okay, you are better than me. This. Like this? Okay, let's be like this. And then?
If you are writing embedding or embedded, then the word D should be there.
I embed, and then I write D there, yes? Okay. Good. So embed K7. It's very bad one. Embed K7 on torus. Okay? Even if you embed on the torus, then you have graph. How many colors you need to cover the case K7? Do I write here K7? If here is K7, we will we have a graph then embedded on the torus which needs 7 colors. So 4-color theorem will not hold for the torus. There will be 7-color theorem. Maybe if we prove it. And what about projective plane? Do you know what is projective plane? So you have one, you take one disk, and now you identify opposite vertices. That's a non-orientable surface. Torus is orientable surface of genus 2, of Euler genus 2. And this is non-orientable surface of Euler genus 1. Okay? And I can now embed in the projective plane, I can embed K6, for example. Now, I will use the other colors. Now, I will go like this, and then I will show up diametrically, and I will come to here, yes. Now, I will show with green. And then I will show up diametrically, and I will come here. Okay? Take black, or no, this. Now we have this one, green one, we have brown. I will go like this, and then I will show up here. And I will go like this, I will show up here. Sorry?
What kind of surface is that?
Projective plane. If you take Nordhus later and you stick around one disk, or just take a disk, ordinary disk, and identify diagonal vertices. A, B, B, C, C, D, D. So you identify opposite vertices. This has a cross capice, call it, yes. This is non-orientable surface. You cannot draw it in these 3 days. And
What are we actually doing in embedding?
sorry?
What are we actually doing in embedding?
We draw it this graph K6 on the projective plane. So K6, this graph is K6, you see? 1, 2, 3, 4, 5, 6. And every vertex with everyone is drawn. So in the embedding we want to draw the graph not crossing the edges. The same is in the plane, on the sphere. We want to draw some graph, if possible, that edges are not crossing somehow. Okay, and now we embedded K6 into the projective plane. This is a surface with Euler genus 1. You don't understand these things? Here are these things. Look. Do you see it? Let's see. You see? Here's K6. And then when I go here, I got diagonally come here. When I go here, I can diagonally here. So every 2 vertices are adjacent. Here is a K7, which is this surface. When I identify this one with this one, and this one with this one I identify. I get cylinder and I identify like this, then I get torus. Okay?
You should be able to draw that on torus without edges being crossed.
Yeah.
So that is not clear from the picture.
Which one?
K7 in torus, I think.
This is clear. First, this picture is clear. Let's, if I go vice 4, come diagonally and I proceed and come to here. This is a vertex from A to B. Okay, do we agree with that?
So basically, sir, is there a Mobius strip from that 4 to that we had the thing?
So Mobius strip here, we can go at this if we take Mobius strip and one disk and they glue it together. Or just taking disk and glue up diagonal vertices, which is kind of the same. Okay? You never did this topology, I don't know, topology 1, 2. This should be in topology taught. You didn't have course topology? So if you go like this and you come diagonally, come here and you proceed this. This is C. This edge connect B and C. Okay, and so on. And this is embedding on K6 on projective plane. Now question is, we can say chromatic number of the surface of the sphere is how much? How much? How much? 4. 4 out of 2. Now question, we have this projective plane. What is the chromatic number of projective plane? Let's see the biggest chromatic number amongst all the lines that we can draw on the projective plane. We go out to linearity now, we study other surfaces. What we did for the plane, for the sphere, you can do also for the projective plane, for torus, for double torus, for triple torus, for plane battle, and so on. So what is something that corresponding to the theorem in the projective plane? You see we have here K6 embedded. So what does it mean? We have graphs on the projective plane which need 6 colors. That's K6. Do we have graph on the projective plane that needs 7 colors? Or maybe 8? Or maybe 9? Can we answer this? And then we go to the torus. Torus. It's a little bit ugly written, drawn. There are some other drawings a little bit nicer. And this is embedding of K7 on the torus. Now I ask, what will be the chromatic number of the torus? Will it be 7? Or maybe 8? I know it will be at least 7. K7 I can draw on the torus. K7 needs 7 colors. But can I draw K8 on the torus or K9 or whatever? Can I have a graph which needs 8 colors on the torus? So actually surface, the plane, the sphere is only beginning. We have all these surfaces and we can try to answer them, yes? What is the maximum chromatic number we need on some surface? That is no more than 100 years. It's much easier than the 4-color theorem. That was done by, this is here, no, we go back. This is this theorem. 100, he is by the way Englishman. Maybe he has been to India in that time. So Heawood in 1890 proved that if we have G embedded on a surface S with the Euler genus bigger than 0, sphere has of the plane has Euler genus 0. Projective plane is Euler genus 1. Torus and Klein battle. Klein battle also cannot be embedded in this studio. They have Euler genus 2. And so on. Okay? Now, Heawood proved that if I have surface, doesn't matter orientable or non-orientable, with Euler genus G, let's be strictly than 0, we have chromatic number is bounded by this strange number. And now put here 0. Put here 0 for the plane, for the surface. What do you get? 4. Do you think this is short proof of the 4-color theorem? This proof doesn't work for the 4-color theorem. But number coincide. This argument, which is like 10 lines argument, prove this. It's a famous theorem of Heawood. But if you glue G0 here, you get 4, which is also for the plane, but we should prove the 4-color theorem differently. This is not okay. And we will see why not.
Genus and Euler genus are different things?
Euler genus is derived from genus
Genus
in order to unify orientable and non-orientable surfaces. So we can define like this. Euler genus is equal to twice the genus if S is orientable, and is equal to the genus if S is non-orientable. It is more convenient for graph theory people to do this way, yes.
Genus, I read that number of holes in the surface. Like the void has one hole in it.
No, I mean for orientable surface, we have like this. We have one handle, another handle, and another handle. So for orientable surface, it is actually the number of G is the number of handles. So torus has genus 1 handle. But Euler genus is actually, we count these holes here when we remove it. So it will be 2. Now, if we have two non-orientable surfaces, we have sphere, and we have this, we cut it here and we glue Mobius or identify opposite things, it is one cross cap. So one cross cap, as a non-orientable surface, projective plane has genus 1. It has one cross cap. If I cut it out, there will be one hole. Yes. This will be claim bottle 2. So it is it. Euler genus counts the number of holes, which comes to be twice the number of genus for orientable and equal to the genus for non-orientable. Okay? So let's make this proof of Heawood. This number is called Heawood number. Okay? This. Okay? Let's prove it. We say let's we go by contradiction. Let G has chromatic number, okay, bigger than H G, okay? And if we plug here for 1, we get 6, okay? Okay? So we can assume that G is embedded on the surface and chromatic number of G, as I said, is bigger than Hg, yes. So it is implies that chromatic number of G is at least 7. Because the lowest bound we have here is 6 for G1. But then it means a number of vertices is bigger than chromatic number of G, which is at least 7. So the number of vertices is also at least 7, yes. We don't need bitwise for this. I was like too much writing. Okay. Then we go by contradiction, yes. Okay. We can assume G is critical. We can assume. Okay. We can assume G is K critical. Oh. Okay. Since it is K critical, it has minimum degree K minus 1. So at least K minus 1. That's imply what is the number of edges? What is the number of edges? Twice the number of edges is at least K minus n, yes. Twice the number of edges. So this is twice the number of edges. Okay? Now, what we didn't mention, similarly like Euler formula in the plane, we have Euler formula V minus C plus F equal to 2, okay? On a surface with Euler genus G, we have minus A plus F. Actually, it may not be cell embedding because we have hanging on somewhere, on some faces, some cross caps, hanging on some locally somewhere, some handles. And actually, because of that,
You just said a cross cap.
cross cap, you get it. What I say, if you have a surface, okay, and you have a hole, I cut it a hole. Now I identify opposite vertices. On Nordhus leather, I glue Nordhus leather, yes. And then what we get is called cross cap. So you have ordinary surface, yes, the plane, and I cut a hole and I identify opposite vertices of the border. I will get projective plane. Projective plane surface with 1 cross cap. Claim battle with 2, and so on, okay? So, because I may have my graph have a locally some cross cap, which I don't really use it, yes? So actually, we may have here inequality. If it is two cell embedding, meaning every face is a disk, open disk, from the plane open disk, then we have equality, but nobody says that we must have it. Okay, so we have this Euler formula for surface with Euler genus equal to G. Okay, so we have V minus F plus F is at least 2 minus G, yes? Okay, and this can be written in this way. I can move. Okay, I start using. Look, in this talk, M is equal to E. Yes, just like switch it. I denote it once the number of edges by M. So take this to be the same. Yes. So, I can swap. Okay, let's change it. Let's change it to have everywhere nice. Here should be N, and here should be M. Okay. So what we have that for faces we have again this equality as 3 times faces at least twice the number of edges. Yes, do we agree something like that? Yes, and then faces are actually twice M minus over 3. Yes, we can glue that here. Yes. Okay, then we have that N, this is N minus 2M over 3 plus F should be at least twice G. Okay, no, 2M, this is plus minus, no, from beginning, we have N minus M plus 2M over 3 is at least 2G, and we will simplify N minus M over 3 is at least 2G, and from here we get, I will just write it, M is at most 3M plus 3G minus 6. What?
Lower ones only, how can we be greater?
No. I'm clearing up. Okay? Every face has at least 3 edges.
That means it has to be greater than
Sorry?
every face
F is almost 2M over 3, okay?
at least.
Let's do it. I'm hurrying. Okay, let's say if I sum all faces, I get twice M. Okay, and then for every face, yeah, and this is equal. Then if I put here 3, sometimes it will be 2M.
Yes.
3F is smaller than 2M. F is smaller than 3 over M. Okay? Are we happy? Okay, I'm speeding up because we are running out of time. Yes, this was something what we must did first day, and we get this. Yes. Okay. We get this. Okay. Do we agree up to here? Actually, 2M at most 6M plus 6G minus 12. We need actually this. Now, because we assume graph is critical, 2M is at least K minus 1N. So we have K minus 1N. Okay? So we have this. K minus 1N And this can be written, if I move this on the left side, if I move this on the left side of the inequality, we can have k minus 7n, okay, then minus 6g plus 12. Okay, now this is what we know, this is n. N should be, I think n should be, n, what we have, n is at least k, yes? Do we agree n is at least k?
Yes.
N is at least k, okay? So we're going to have k squared. So if I plug here, k is at least 7. So this is not negative. And n is at least 7. So it will be okay. It will be okay if instead of n I plug here k. It will still hold this inequality, yes? Now, so we have k squared minus 7k minus 6g plus 12 should be smaller than or equal to 0. And then this implies solving this square equation, how you call it this in English. You're gonna get number 7 plus minus, if you solve this, that will be 49 minus, how it call it, minus, how it was 4, a little bit forget it. 4 minus 6g plus 12 or something like that, over 2. But because we want this bound, here comes plus. You should know that better than me. I'm forgetting, I'm old. You get this bound 7 plus inside. This will be something cancelled. It will be 1 plus 24g over 2. So k should be smaller than this in order to hold this inequality 0, and then you round it down, yes, because k is integer, yes. This is how it's obtained, and so, okay, this is bound, which Heawood got it, the famous Heawood bound, yes. Of course, then was question, okay, if we go a little bit back, okay, if G I can draw on S, then this is upper bound. But is this bound achieved for some graphs? We saw it now. For projective plane is achieved, I can draw K6. For torus is achieved, I can draw K7. For claim battle is not achieved. You cannot draw K7 in claim battle. And claim battle is the only exception. For every other surface, how I can write it now? I need space. I can write here. For every other surface, let me take this copy somewhere out. Copy. Add page. So I can paste. Look this. Is it too small, yes? It's better. We said we don't know this number, Heawood number. We said it's equal to this value, yes? We so far know if I can draw G on surface with origin of G, then chromatic number of G is the surface, the Heawood number of G, this value here. So this was very fast argument. He would do it in one day, yes? But afterwards, people wanted to show that this, wondered if this really exists graphs with this chromatic number on that surface. And I said plain bottle exception is only exception. So then they make it, it took like 80 or 100 years later, Ringel and Jung, they prove it that, and some other people with some special cases, they prove it that if we have that complete graph on this number of vertices, on the number of vertices of the Heawood number, can be embedded in this surface, unless SG is plain bottle. Okay? So they invented some method how to do the current graphs, rotation systems, and some things like it's complicated to prove that this graph, complete graph on Heawood number of vertices can be embedded on any surface except plain bottle. Okay? So what's the time? Do you want a small break? Sorry?
Why this proof doesn't work for plane?
This proof doesn't work for plane, I think, because for the plane you cannot assume 7. You cannot assume 7, yes? And then this number k minus 7 then will be not, for other surfaces is non-negative. I mean, here will be negative. If you take like, okay, let's say let's on the plane, chromatic number is at least 5, then 5 minus 7 will be negative. And you cannot n replace, if this is negative, you cannot n replace by k. This is the problem. And just because of this, we have like huge proof of four-color theorem. This doesn't.
In the case, we assume that k will be 7, so 7 minus 7 will be 0, so the proof works.
So for k equal, we assume that k is at least Heawood number plus 1, yes, and 7, then it's still okay. 0 multiply whatever is 0, yes. But it's wrong if it is k minus 7 or negative, then you actually not doing something from here go to something smaller, you go probably something comes wrong, yes, it's negative. Okay, now small break, yes. You maybe have something, I don't know. And then we will proceed with the today topic, which is more like some various questions. We repeat it. We proved Nordhus Gaddum the first day, which we didn't make it. And I prove it now, Heawood bound, yes. An explanation of graph on surfaces embedding the chromatic number, not only of the plane, but on the graphs on higher surfaces, yes. I think it's important they know it. The Heawood bound is very important. And the second hour, we're going to go randomly different kind of colorings. You can come and present something. So what is your coloring? Total coloring or domination, or somewhere here some injective coloring, total coloring? Maybe I didn't remember well. So somebody some kind of square coloring, some new kind of square coloring. It was you will come maybe afternoon and tell me what is it, because I don't know what that. So here we have millions of colorings now. Let's try to invent new one. It's a homework until from the lunch break to give us some new coloring. Okay, it's more yeah?